Hello everybody, in this lecture we will be solving 1987 IMO problem number 6. Here's a view of this problem. N is an integer greater than or equal to 2. Then we would like to prove that this expression, which I will more conveniently call as f of k, if it happens to be prime for k's in this range, integers in this range, then the same expression should be prime for integers in a wider range. So I would like to prove an equivalent statement. It will make use of an extremal argument in the following way. Let m be an integer, obviously, positive integer I assume, the least such that f of m is composite. By the hypothesis here, we know that m must be greater than this expression here, so which implies m is strictly greater than square root n over 3, or equivalently, if you square both sides, we would have that n is less than I think 3m squared. Yeah, we need to show that m happens to be greater than or equal to, so show that m is greater than or equal to n minus 1 here, right? So this is an alternative formulation of the same problem, but somehow we love this formulation because it makes use of this extremal argument that's very useful which is a very useful strategy in problem solving. So because f of m is a composite number, let p be the smallest prime divisor of this number. So let another extremal principle type of argument, and let p be smallest such that p divides f of m, and obviously by a very well-known result, so this implies that because it's the smallest, p is definitely less than or equal to the square root, square root of f of m, right? So divisors of any integer come in pairs where one of the pairs is definitely less than square root of that number. So this implies that p squared is less than or equal to f of m, but recall the definition, recall the definition of f of m, which is m squared plus m plus n. Now I will make the following trick. I will replace n with this expression here, so therefore m squared plus m plus 3m squared, which is 4m squared plus m, and as a result, if I add, so this is definitely less than, knowing that m is a positive integer, less than 4m squared plus 4m plus 1, which is 2m plus 1 squared. And as a result, so p squared being strictly less than this expression here, we can say that, so this implies that p itself is strictly less than 2m plus 1, or you can equivalently say p is less than or equal to 2m. I would like to make a following observation. Please have a look at the following expression here. So consider f of m, which is our composite number, minus f of k. So this is equal to m squared plus m plus n minus k squared minus k minus n. The n's will cancel out, and then I can carefully factorize this expression here. So we have an m minus k times m plus k, and then we still have m minus k plus m minus k. Factor out the m minus k, and we have this m plus k plus 1. I will multiply this expression for k equal from 0, 1 all the way to m minus 1. I will multiply the equations, and we get the following result. So if we multiply out all of these expressions for k equals from 0 to m minus 1, we have f of m minus f of k. This whole thing is equal to the product k equals from 0 to m minus 1 of this thing here, m minus k times m plus k plus 1. Let's plug in some numbers and see if we can get the pattern here. So if I plug in 0, I get m here, and then I get m plus 1. So let me write that down, m times m plus 1. If I plug in 1, I get m minus 1 times m plus 2, and so on. And if I plug in m minus 1, I'll get m minus 1 would be just a 1. And then here it would be 2m minus, so just 2m times 2m. Do you see the pattern? So we have m minus 1, it keeps falling down until we go to 1. And then this one is m plus 1, m plus 2, all the way to 2m. So basically we are tracing out all the numbers from 1 all the way to 2m, multiplying them out, which is simply equal to 2m factorial. We know that 2m factorial is definitely divisible by p, right? Because it contains p itself. So let's write that down. Yeah, p divides 2m factorial, since p is less than or equal to 2m, first of all. What it implies next is that p will surely divide one of these expressions, not all of them. So there exists an L in this range from 0 to m minus 1, such that p divides it, right? So p divides m minus L times m plus L plus 1, suggesting that implying that the greater one is this one. So p must be less than or equal to m plus L plus 1. And recast it in the following way. So this thing is, remember, it is just f of m minus f of L. So we know that p divides f of m, so that's the premise we started with. So p divides f of m, and also p divides this expression, and p divides f of m minus f of L. So this implies that p divides f of L. But wait, L is less than m, obviously, in this range, but we know that for those numbers, m is the least integer such that f of m is composite, suggesting that where f of m is prime, so this is a prime number. So therefore, p is actually equal to f of L. And so we can say, therefore, that equivalently, by the definition of f function, so we get that this is L squared plus L plus n, which therefore implies that p minus L is equal to L squared plus n. Now combine this with this, so recasting this one as p minus L is less than or equal to m plus 1. So therefore we get that, so m plus 1 is definitely greater than or equal to p minus L, which is equal to L squared plus n. But that thing is obviously greater than or equal to n itself, suggesting that m plus 1 is greater than or equal to n, which is exactly what we wanted to show to begin with. Remember, that was the main statement that we wanted to prove, that we showed that m must be greater than or equal to n minus 1, and we're done.